I think we all know Andris, or we have met him yesterday. But so he's going to talk today about his work. I think on how to do high flow self-consistent. I think that's
yes, various things. Yes.
So please go.
Okay. Thank you. Thanks, Felix. So I'm going to talk about various issues or aspects of gyrokinetic modeling for simulations in situations where one might have large amplitudes or large flows. And so our immediate motivation is that there are people I work with who are interested in doing kinetic edge simulations with gyrokinetics. And so that poses several problems for gyrokinetic models. The most obvious one is the large amplitudes. For example, a simple instance of this is if you look at the gyrokinetic Poisson or vorticity equation in its simplest sort of long wavelength form, it looks like this. It's a divergence of a density and a gradient of phi equal to some source. And this density evolves both due to nonlinear fluctuations and through sort of through sort of secular evolution also. So here's an example from a 3D fluid simulation of a D3D edge region with the Bout code. And what this mainly shows, if you look at the black curve, which shows the relative change after some time of the density profile from the initial state in the edge region, it shows that there's order 1 evolution of that profile during the time of the simulation. And so in a sense, what we're trying to do with kinetic edge simulation is sort of a kinetic generalization, a kinetic extension of something like this Bout code, which has found fairly wide use already in the United States. In addition to large perturbations, one may also have large time-dependent E cross B flows, which are even more of a challenge. And I'll discuss issues connected with both of those. So here's the outline of the talk. First, this talk sort of will proceed from sort of the more practical and tractable topics to the more difficult. So in terms of more practical, there are sort of easier extended orderings beyond what's sort of considered the standard gyrokinetic ordering. And I'll discuss some subsidiary orderings for the electromagnetic perturbations that simplify the model with respect to those. Even in the simplest form, a gyrokinetic model for a situation like an edge plasma will need to include the second order terms. And to date, to my knowledge, no gyrokinetic codes really implement those. No one's really attempted it. So there are issues connected with numerical discretization of those second order terms. So how do you do that? And then the last topic will be gyrokinetics in sort of what is, in a sense, the most general possible low frequency ordering. So within the framework of a low frequency gyrokinetic ordering, what are the minimal constraints, and how does the theory work out, and how does it look?
Those are second order terms in the Hamiltonian? Or?
Yes, second order terms in the Hamiltonian, and you can variously categorize them as first order or second order terms in the gyrokinetic Poisson equation. Certainly. So I'll show you those explicitly.
Doesn't Bruce Scott do second order terms?
I haven't seen his recent work with gyrokinetics. Yeah, I'll have to look.
His second order terms are at a 0 FLRFF.
So long wavelength,
Yeah.
you say. Yeah, so for example, in the Bout code, you already have some second order terms, such as the Poisson equation, that large density variation term. That can be thought of as one of the new terms. So in the long wavelength limit, yes. I mean, in the long wavelength limit, people have done it. But I guess, if Bruce has circulated recent work, I'm maybe need to check it. Sorry. So prior to our involvement with this, I had done some work in 1992 with Linda Lodestro and Dan Dubin, where we extended the ordering in a Hamiltonian, in a canonical Hamiltonian theory. And I apologize, I brought the wrong power supply to my computer here, so I didn't have time to clean up the talk. And one of the things, the PDF converter converted things like much less than signs to equals signs, which is sort of unfortunate, a very unfortunate substitution.
That's how you deal with the second order terms.
So ask if anything looks confusing in the orderings, ask me. So the new ordering is actually that the new ordering parameter is V E cross B divided by V thermal is much less than 1. That's the ordering parameter in this theory. And it allows for E phi over T, the electrostatic potential relative to the temperature, to be of order 1. And so we worked this out in a slab theory in 1992, and that derivation, it worked out fairly nicely, except the way I did it. It had some issues with energy conservation, in addition to being a slab theory. So that's one of the topics I'll talk about. Then, in terms of attempts to actually include large flows of order the thermal velocity, there's there've been quite a few people who've worked on it, and this is probably not an exhaustive list, but the first one I'm aware of is Artun and Tang, who in a standard recursive gyrokinetic theory addressed large flows. And then there was a Hamiltonian work by Brazard and sort of extensions and applications of it by Ham in particular and co-workers. And then there's a work by Hong Chen also, or probably more than one on this issue. So one thing I was interested in ever since this work was actually a theory which this work sort of predated those, but then how do you actually do this? And so these people worked out an approach, but those theories were sort of used a two-scale separation of the potential and were also assumed it was static. So I always thought a more general version of it should be possible, but I didn't have a chance to do it until the last couple of years. So first I'll discuss the extension of this 1992 work by myself and Dubin and Lodestro to general geometry. Basically, again, the ordering. So I'll mainly show the results for this, and for derivations, I'll show some derivations for the most general theory. But this one is actually very, very easy. There's only one sort of step that's a little different from what the standard theories used. So the ordering is that this, again, the normalized potential here, this is an electromagnetic generalization of phi, is much less than the thermal velocity, much less than the thermal level, and the associated E cross B velocity normalized to thermal is much less than 1, and that's the ordering parameter. And the key way you capture that in the theory is, as the small parameter is that before you do your Lie transform perturbation theory, you separate this psi, in this case, into its gyrophase averaged piece and the remainder, and this remainder is of this size, of the size of this small parameter.
And just to understand your very first equation, Q psi over T is allowed to be order 1.
Yes. Sorry. Yeah, sorry about there are various character substitutions that have sort of happened randomly. So here's the result. And actually, having done that, the theory goes through with essentially no difficulty in the same way as was done by Drazard and Harm and others. So here's the result to second order. This is a canonical p-parallel version of the theory. So it has all of the standard terms, same energy conservation relations as in the standard theory. And the only thing we had to do was this separation at the beginning. In the 1992 work, I chose this to be this piece to be a guiding center potential instead of the gyrophase average, and that actually made it more difficult to sort of have a nice theory with energy conservation. It was just had to work harder. So this choice is actually better. So up to first order, the Lagrangian just has all of the standard terms that you expect, including the parallel. So here for the rate of spatial, or the gyrocenter velocity, you have parallel streaming, E cross B drift, grad B drift, and curvature drift. So it has all the standard things. And at second order, it has, again, all the well-known terms in the gyrokinetic theory. But the one thing, now I mentioned these second order terms that, again, have really not been implemented before. And so in the gyrocenter equations of motion, there are these quadratic terms. And now if you take this result from the previous slide and you make the full sort of variational theory for it, that gives you a variational derivation of the whole system, and therefore you can apply Noether's theorem and derive the conserved energy. You find that what you need to have the conserved energy includes includes the size, the electromagnetic pieces in the gyrokinetic Poisson equation, and also first order pullback transformation pieces in the current that goes into the Ampere's law. So a simplification which for numerical purposes might be useful is what I called these practical minimal models. And what that does is, what those do is basically just promote or demote some of the electromagnetic terms to higher order. So in this case, specifically, you can still keep your gyro average of the perturbed parallel potential to be of order 1, but promote it or demote its gyrophase variation to order epsilon squared. And the resulting theory removes the electromagnetic sort of current terms that would arise in the gyrokinetic Poisson equation, and it also removes the everything but the identity part of the pullback transformation in the current equation. And then this whole system, the equations of motion that result from this Lagrangian and these two field equations then still have a nice conserved energy, and it's all consistent.
When you say that delta A parallel average is of order 1,
Mhm.
that's taking into account that the guiding center background A is of order epsilon to the negative 1.
Yes.
Yeah.
Yes. Yeah, I've sort of done that implicitly, I guess.
And just so
Sorry.
I'm clear, you can describe what you did here just in terms of modifying the Hamiltonian.
Yes.
Then you derive-
That's right. Sorry. Right. This is sort of it's a canonical version of the theory that I.
So then you derive your equations from that approximated Hamiltonian.
Yes. And I guess it's sort of the standard thing that there's, there's geometry in the equilibrium magnetic potential here. So.
I didn't understand how that related to my question.
Oh, just in the sense that the geometric terms involve these symplectic pieces, I guess. So that when you do the Euler-Lagrange equations, it's the geometry, comes out of the dr piece. It's just that it's not a slab field, so there are non-trivial things that go on there also.
Does this approximation have any sort of physical interpretation? So this ordering on the top line.
It would say that at some level, I'm not sure what a good interpretation for it would be. It still allows the gyro average to be sort of at the nominal order of the full theory, but it just affects the gyro phase dependent piece.
Well, delta A tilde parallel is essentially the gyro radius cross B dotted the perturbed perpendicular magnetic field. So what you're saying is that in a small gyro radius limit, that's going to be small.
I think there are sort of not really any conventional terms that people are used to that you'd associate with that term, because they're all at the second order in the gyrokinetic Hamiltonian, and no one has done that I know of has done much in the way of heuristically interpreting those terms. Perhaps in your back in John's days with Dan,
Well, let's see. I mean,
there's sort of ponderomotive.
Some second order terms are related to Reynolds stresses. And does this have to do with evaluating them in the presence of bending field lines, or?
So I don't know the answer, but they're at the level of as I say, they're in the second order terms in the theory, and so they're already they're sort of unconventional in terms of, say, core theory. You wouldn't even have the terms that make a difference, I think.
What is the magnitude of delta phi tilde?
Delta phi tilde is order epsilon. So that's the sort of E cross B drift, the size of the E cross B drift divided by the thermal speed.
Somehow you are assuming delta. Normally, delta A parallel and delta phi are comparable in this.
Yeah. I think the raw theory just put them at the same order, as in, say, the Harmly-Brizard work, as in our version of the Harmly-Brizard. You could have them at the same order.
I think this is actually a long wavelength approximation for delta A, but not for delta phi.
So as I said, the nice thing is that it gives you energy conservation. One of the nice things was that you don't have to have these additional terms in the current when you calculate it for Ampere's law. and you still have a nice system.
Those additional terms look just like terms you have to deal with involving phi.
Yes.
Above.
Yeah.
So you just
But there are more of them, and
you just call another subroutine with a different argument.
yes, certainly in the case of phi, perhaps it's not so much the case for Ampere's law, but in the case of phi, those terms are the most challenging. Especially the pieces associated with perturbations of f, are the most challenging ones. So perhaps here you'd have to explicitly evaluate them, which I think you don't want to do unless you have to, because even the evaluation is expensive. And I'll get to terms like that in a couple of slides. So any of the, even at this level, one would need to include some of the second order terms in the gyrokinetic equations if one wants to go to perturbations of order, potentially of order 1 in the model. So there are two sets of terms, of course. There's the ones in the gyrocenter equations of motion and the ones in the field equation. Now, the treatment of the first order terms in the gyrocenter equations of motion is standard, a completely standard thing. All the codes have some way of doing that involves either gyro averaging over a gyro orbit or for example, using Bessel functions in Fourier space, or some treatment of that. So that's
How widely used is that last option?
Sorry?
How widely used is the option you just said with Bessel functions?
You would know better than I do.
Okay, I thought it was only one.
Yeah. So I'm just saying there's nothing new at that level, but for the standard terms. But then once you get to second order, you need at least some extension of those methods. So here's an example, the second order terms in the equation of motion. There's the d by d mu term, and this is the gyro phase average of the square of the gyro phase dependent part of the perturbation. This you can either evaluate somewhat directly or use this relation. And then the d by d mu derivatives you can resolve, you can express in terms of spatial derivatives on the function. And so with a combination of just differencing or Fourier analysis and a standard gyro average, you can evaluate those terms. So the other kind of term that arises at second order in the equations of motion.
Excuse me, Andris, I'm now lost a bit. Second order terms in the equations of motion come from third order terms in the Hamiltonian?
No, these are. I'm referring to second order terms in the Hamiltonian.
Oh, okay.
So.
Okay, because that's different.
So yeah, sorry. So second order terms in the Hamiltonian. So the terms that correspond to those in the equations of motion. So this kind of term, here you have a gyro phase dependent piece of the perturbation, a derivative, and this is the indefinite integral of this with respect to gyro phase angle. So formally you can write this as something like this. So you have actually a double integral over two gyro phase angles, and by symmetry, so there are derivatives which will involve some sort of differencing operation with respect to the potential, but then by symmetry it turns out that in this θ1, θ2 space you only need half of the square essentially. So here I've normalized the thetas to 1. So in a case, as I've sort of shown on this diagram, where for the standard gyro averaging you'd have 4 points, for this double integral you need 10 points. So this is the relationship. If in the standard gyro averaging, you have n points. It's n plus 1 over 2 for this double integral, for approximating this double integral. Then the third issue is the terms in the gyrokinetic Poisson equation. And those can, as it turns out, be directly discretized. The issue is that...
Sorry, in the previous slide, sometimes convolutions are done faster in different spaces.
You mean like these...
Well, so instead of the convolution, why don't you go back to the very first term you wrote down? If you know phi tilde and capital phi tilde,
Mm-hmm.
then you just multiply, take their gradients and multiply them. Doesn't involve a convolution.
I think, yeah. I think that. So if you know phi tilde, how did you know phi tilde? So that involved an indefinite integral with respect to this in the first place.
So you still had to do two 1D integrals in theta.
Yes.
But at least you don't have to do a 2D convolution. Well, there's integral,
Yeah, that may.
integral theta 1
Okay.
and integral theta 2.
So so you're saying for n large maybe that has a better scaling. Yeah. Mm-hmm.
Linear
Okay, I agree.
Instead of,
Yeah.
oh, good. Okay, let's go on.
So I thought for this number of points, even 36, maybe that will give you some improvement over this procedure. So for the Poisson equation, again, there may be other ways to do it, but the issue is that now for if you have order 1 perturbations, then this is no longer close to an equilibrium. It's no longer close to Maxwellian. So the operator associated with this, the operator or the matrix associated with it, however you discretize it, is going to evolve. And furthermore, it's not as trivial to calculate as in the case of a uniform Maxwellian, which is essentially what most of the codes sort of reduce their Poisson equation to. So one way to do it, and again, this may not be the only way, I just wanted to be sure that there was a direct way that's fairly efficient, it is with finite elements. So here's the basic equation. L phi is equal to a source. The linear operator L can be written like this. And here's the source for the case of a single ion species. And so for a finite element method, one basically uses takes the variation of a discretization of the weak form of the equation. So in other words, if you start with a variational formulation that gives you the correct gyrokinetic Poisson equation, and here's one way to do it, and there are others published in both by Alain Brizard and Sagama that you could just apply directly. One takes this variational form, one inserts a Galerkin discretization of the potential, and here are the basis functions. So it's a sum of coefficients and basis functions. And the basis functions usually in most finite element schemes tend to be fairly local objects, which is useful for this purpose. And then one takes the variation to get a matrix equation, and now all of the derivatives in the operator and the integrals around gyro orbits and so on, all of the things that went on in the operator are now resolved onto the basis functions in some way to give you these matrix elements. And these matrix elements have to be calculated in principle real time, every time step. That may depend on the details of the time evolution scheme, but in principle every time step. And the key thing about these matrices is that they, even though they're not as sparse, they're not sparse in the sense of being very close to tridiagonal, they're still quite sparse. So for example, if one's solving the gyrokinetic Poisson equation on a 2D slice, it's basically a 2D equation with, say, 100 cells on a side, with n cells on a side, so there are n squared cells. Each spatial point is coupled through this matrix to about somewhere of order, and if the grid cells are of order the gyroradius size, each grid cell is coupled to about 100 or somewhere between perhaps 30 and 100 other spatial points through this matrix. So that's a characterization of the sparseness. So maybe of order 10 to the 2 times n squared non-zero matrix elements are needed instead of a dense matrix would have n to the 4th. So say for 100, so if the your plane is 100 cells on the side, this is, 10 to the 100 times cheaper than, or 100 times fewer elements than a dense matrix would have.
What do you know about the conditioning of the matrix?
I think usually I'd expect it to be very good. I mean, just based on the core theory that the matrices really don't pose a problem. They never have, and unless the equilibrium, unless your F really does something very extreme, I don't think the conditioning will go bad. That's sort of intuition. I haven't proved it, but I expect it to be generally pretty good.
So if you want to exploit the sparsity, then,
Sorry?
if you want to exploit the sparsity using some kind of iterative solution methods,
Mm-hmm.
then you need to worry about the conditioning.
Yeah. No, I think you expect it to be fairly, so for example, in the core case, there are very simple, good Pardé approximations that lend themselves to direct tridiagonal solves and things of that sort. And I think even though the matrix fills out, I don't think it'll become much worse than in the core case, unless the distribution function does something very pathological. But I don't know for sure. No one's had experience with this, and I don't have a sort of an analytical proof. So the last thing I'll talk about is sort of the most general version of the low-frequency gyrokinetic theory. So ever since the 1992 work, I've always thought that one should be able to do better in the ordering, and in fact, all the work since Artun, in some sense, Artun and company has shown that you should be able to go to a situation where you have large flows. Just considering the electrostatic case, the absolute value of the potential shouldn't matter, and even if there's an E cross B drift, at least locally, that shouldn't matter in terms of it shouldn't matter for the validity of the gyrokinetic theory, because if you just go to a locally drifting frame, provided the shear is small enough, then the gyro orbit should be well defined, and mu should be an adiabatic invariant, and so on. So one would want a theory that has the basic ordering that the E cross B shear normalized to the gyro frequency is a small parameter, and to do it in such a way that it allows for flows that are order 1 compared to the thermal, and consistent with these two things, that actually you want the potential to be of order epsilon minus 1. So we have a slab electrostatic version of the theory that I've discussed and is published in a March paper, and I'll just go through the results there briefly. So here's the Lagrangian. U is a gyro average D cross B drift. The key thing to note about it is that it has some new kinds of components that didn't appear in any of the previous works with large flows. So in particular, these terms that be rho and spatial derivatives of U and gyrophase dependent pieces of phi didn't seem to be there. And in fact, these are formally of the same order as the terms that are kept. They're actual, at least from an ordering standpoint, they're second order terms. So at up to first order, you take the Euler-Lagrange equations and invert them and get the equations of motion. And here's the main equation that matters, I guess, is that for the evolution of the gyro center position. And that has the E cross B drift and parallel streaming and the polarization drift. And it's worth noting that pieces of this polarization drift were in the previous large flow theories, for example, of Brizard and Harm. But these two pieces are sort of, in some sense, especially this one, is a generalization for the time-dependent case, where your large flow is allowed to be time-dependent. So to get the equations of motion at second order is a bit more complicated because there are new terms in the sort of new non-canonical terms that actually make the make deriving the equations somewhat harder. The simplest way to do it is to actually apply perturbation theory, again in the gyrokinetic parameter, to the Euler-Lagrange equations themselves, and those have the character, the Euler-Lagrange equations have, Z dot is equal to the Poisson matrix times dotted into the derivatives with respect to the Z's of the Hamiltonian and time derivatives of the symplectic pieces in the Lagrangian. And so you have to invert this matrix, and the simplest way to do it is perturbatively, and here's the result. And doing so, one can get the second order contributions to the equations of motion. If one actually wants to do it directly, get the equations directly, which may be useful because then you know that they'll satisfy whatever conservation properties the Hamiltonian system had at some level, at least analytically. Then it becomes much messier, and here's a sort of a Mathematica rendering of the first row of the inverse of this omega matrix, or the first row of the Poisson matrix, and with the symmetries and so on taken into account, and it's much denser than the canonical case. And each term involves quite a few things to evaluate that involve derivatives and so on. So it's sort of a messy object. And then finally, I have a correct, this slide was a casualty of my not having my laptop battery to fix it. But the key thing is that the gyrokinetic Poisson equation actually, and this is a result I've been able to show since the paper was published, it actually is to linear order in phi, it is exactly equivalent to the standard form. So this was actually the old version of the equation that's published. But if you calculate the Jacobian correctly, and that has this gyrophase dependent piece, and do a couple of partial integrations, and just work to linear order in phi, it gives exactly the standard form of the gyrokinetic Poisson equation, which is nice because until I showed that, I was concerned that maybe by going to this ordering, you might lose some terms that are present in the conventional theory, but that doesn't seem to be the case. So we've done a toroidal electromagnetic derivation, and I don't know how much time should I take.
Well, you could continue.
I can continue a bit. And I'll go through the derivation a little bit. So that works. Basically, the idea of the procedure, it's certainly not new now. Again, the first I saw it was in the earliest I've seen is in Artun's work, and then Alain Brizard did a Hamiltonian version of that. But the idea is that you the key sort of calculational step is that you transform to variables such that your velocity variable is in a drifting frame, and it turns out to make things work, that frame has to be an effective E cross B velocity, which it would work not as elegantly. If any of this is elegant, I don't know, but it's actually messier if you use the guiding center position here, but it'll still work out, I think. But I think the most convenient is to use the lowest order gyrophase averaged E cross B velocity for this transformed variable. And the way you can define this and show that such a transformation is well defined is that in your transformed velocity, with your transformed velocity variable, you define a gyro radius vector, you define a magnetic moment, you define this gyrophase averaged field from phi, sort of at a given value of the modulus of rho. You define this field, and you define the associated E cross B velocity associated with this field, and then everything's sort of forced to be internally consistent with this equation, for example. So, because you need your velocity variable plus the transformed one to be consistent with the physical velocity, and it turns out that the solution of this is this equation. With these definitions is well defined because of the ordering, basically. And again, this is a case where it should be much less than. So you insert these variables into the standard electromagnetic Lagrangian, and again, take the Euler-Lagrange equations. Sorry, this is just transforming from the lab frame V to your new V variable. The Euler-Lagrange equation indeed gives you x dot as u plus V, again because this matrix is much smaller than the identity, so it doesn't mess up the inversion of the sum of the two. And then the additional thing that's used in the theory is in calculating generating functions as a point where you get advective derivatives, and it's that advective derivative that is constrained to be small rather than just the partial derivative. And then additional point for doing the general magnetic field case is that, in fact, when the derivation that I do is sort of one step in the sense that the standard derivations have all typically first derived a guiding center theory, and then added the perturbations and done Lie transform kind of on top of the guiding center theory. And that's actually the place where the two-step procedure actually loses terms such as those rho dot grad u phi tilde gyro average term. So that's where those got lost in that two-step process. So we're using a one-step derivation. And so the lowest order transformation, one uses those sort of lowest order guiding center variables, and this is the resulting Lagrangian. Then the separation of phi is into a gyrophase average plus the first sort of Taylor series term in rho plus the remainder. And then this remainder is the size of the remainder is the size of is the small parameter. The remainder happens to be the size of the small parameter if you do this. And then you will eliminate this term, and this term actually cancel nicely provided this is satisfied. So that's where you need a very particular choice of u to make the theory work. And then having done that, you get sort of your lowest order guiding center Lagrangian. And the additional comment I have was that here I've separated the profile scales from the major radius scale, which I take as the scale of spatial variation of magnetic field by an order of epsilon. And that's because if you don't do that, it turns out in this one-step derivation you get a whole bunch of extra terms at the order of terms that you would keep. And so I think the theory would still go through, and I believe that the next talk may address that issue also. And actually, from what I understand, you've been braver than I have. But I've worked out this theory in this ordering, which is actually sort of somewhat well motivated by edge conditions. And so here are the guiding center Lagrangians in the sort of canonical p-parallel and non-canonical p-parallel versions. And even there's sort of, in this case, there's a new term that pops up at an order that will be kept. Go through the Lie transform perturbation theory on one of those Lagrangians, and the key results that I use are, I guess, summarized here. Mainly, you'll apply the first order piece to get this first order generating function, and that's used to, for example, calculate the L1 gamma 1 that you need to get the second order. Sorry. To get the second order Lagrangian. And so you get equations for the generating function, and in particular the time derivative, one of those gives you a PDE for the generating function, and that has slow pieces plus this equals delta psi. That gives you the generating function, and that gives you this S1, the gauge function, which gives you the generating functions, and out come the second order pieces and the first order pieces of the Lagrangian. So just a comment, as I said, the core ordering where you collapse the profile and magnetic field variation scales actually is much harder. And it brings in things like FLR corrections to the involving the equilibrium magnetic field, higher order equilibrium terms, and a lot of terms that I characterize in this way as sort of couplings of the equilibrium magnetic field variation and fluctuations. So I'll go on to sort of just to summarize what I've talked about. So in terms of practical models that could be implemented soon, this Dimits-Dubin-Lodestro ordering version version of the theory should be workable. So, actually the next, again, this is a better version of the slide. I discussed numerical algorithms for the discretization of the second order terms that would come up, and also discussed a more general theory that allows for large flows. And that theory is, it still has significant challenges just from, the standpoint of how one would implement it. So I'll finish there.